All right, for those on Zoom, I'll just kind of mention what I mentioned to the class here. For those who are coming in person on class on Wednesday, there will be kind of a handout like this that has a lot of the questions that we'll go over chapter 13 that you can pick up when you come into class. For those who are just taking the course online or who are coming in on Wednesday and want to use this already, it's available on Canvas. This little handout, as well as solutions, are on Canvas as well. I mean, not detailed solutions, but at least the numerical answers to the questions are available on Canvas as well. So, yeah, so go ahead and get going today. So before we do, Riley here, just say a couple words about SI sessions.
Over here, I guess, so the Zoom people can hear me. I don't know how far the mic reaches, but yeah. Hopefully the Zoom people can hear me as well. Right here. Okay, whatever. So SI sessions did start this week. I see a few people in here that were in my 9 a.m. session, so hello again to y'all. But so SI sessions do start this week, so make sure that y'all are attending the session that you signed up for. I've actually received a few emails from people that were unable to sign up for sessions. Maybe you forgot, or like you didn't access the link or something. It happens. So just you have to email me, and I have to manually place you into the sessions to make sure that y'all are doing that. I had a few people ask me if they can just attend any session following the link. And you kind of want to attend the session you sign up for. The reason that there's seats and there's a particular number of people that can attend each one is so y'all can do group work and breakout rooms and stuff, and we can have discussions. That won't really work well if there's like 100 people in the session, plus we'll get like a lot of lag, right? So yeah, attend the session you signed up for. If you weren't able to sign up, go ahead and email me, right? And we can get that worked out for y'all as soon as possible. Cool. Are there any questions so far? No, good. Okay, I look forward to seeing you on session tomorrow.
All right, thank you. Yeah, make sure you are attending those. Not only is it beneficial for you, but it is also part of your grade, right? To attend 10 sessions before, I forget the date now, it's in the syllabus, but sometime in November, like the 10th or 11th or 2nd. November 9th, there you go. So yeah, so 10 sessions before November 9th, and you cannot attend more than 2 hours worth of sessions, so 2 sessions a week. So you won't be able to try to like do all 10 hours in 1 week or something like that. Not going to happen. You will only get 2 hours of that counted towards your attendance for the grade, for the SI portion of your grade, right? SI attendance portion of your grade, which is I think 5% if I recall. Okay. All right. So we are starting chapter 13. I posted, I think Thursday or Friday, I forget, last week, videos related with chapter 13, okay, going over a lot of the concepts and ideas involved in chapter 13, talking about solutions and properties of them, okay? I highly suggest that you check out those videos, look at the lecture slides, read textbook, things of that nature, okay, to help with kind of making sure we're following along with what we're talking about and what we're doing in class and why we're doing it, okay, right? So, right, solutions, okay, well, first just talking about how things form solutions, why certain things form solutions, why certain things don't. Oh, right, this screen is frozen. There we go. I'll fix that, those in person here. So the first thing we talked about, we started off in this course talking about intermolecular forces, right, is whether or not things form solution very much depend on intermolecular forces, right? Before, we've talked mainly about what are the intermolecular forces between a molecule and an identical version of itself, right? What are the forces involved in CH4 and CH4, or CO2 and CO2, or H2O and H2O, right? Now, when we're forming solutions, we're mixing things together, right? And if we're mixing things together, we need to start thinking about what are the intermolecular forces between the stuff that's being mixed, right? So not only do we need to care about the intermolecular forces between solute, solvent molecules, we also need to consider the intermolecular forces between the solute and solvent molecules, right? So for example, right, if I have solutions of, say, heptane with pentane, right, therefore, those molecules, right, and their dispersion, right, acetone and chloroform would have dipole-dipole interactions between each other, right? Ethanol, water would have hydrogen bonding, and then something like sodium and water, right, would have ion dipole type intermolecular forces. Okay, right. So again, we have to consider what are those intermolecular forces between the two different molecules, right, compared to then the forces between the solute, and solvent. Okay? And those comparisons leads to kind of this general phrase, right? Like dissolves like, right? Right, polar ionic compounds dissolve in polar solvents, right? Things that have hydrogen bonding and dipole-dipole interactions will mix with other things that have hydrogen bonding or dipole-dipole interactions or with ionic compounds. Things that are non-polar, that have just dispersion interactions, will mix with other things that have just dispersion forces. Okay? Right, and why that is explained more again on the videos that are available online. Okay, and I sent out an announcement. Oh, brief side note, right? At least for me, when I try to click on the links in Canvas, it then like has an issue and doesn't actually load the videos through Canvas. I don't know if everyone has that issue. I've been trying to work to how to resolve it. But what you can do is when you click on the link of the video, and then it opens up a page on Canvas, and it's like, can't open up the YouTube link. On the top, you can click on the title of the YouTube video, and that will take you to a new page that will take you directly to YouTube and open up that specific video on YouTube. Okay. So yeah, if it doesn't open the video within Canvas, you can always go and click on, do an extra click, if you will, and it will take you to YouTube itself, and that will definitely open up the video. Or you can just go to YouTube and check them out. Right, the lecture videos on chapter 13, I try to have, right, all the lecture videos are labeled by chapter, and then I have like, 1, 2, 3, 4, 5 to give an indication of where the sequence each video falls, right, plus then a list of what topics are covered in that video. Okay. All right. So, right, what out of these two molecules here, right, which molecule would be more soluble in water, right? The first molecule here or the second molecule? Second one. First molecule here, cyclohexane. 2, 3, 4, 5. See here. So cycloheptane. Right, but right, this first molecule here has just dispersion type intermolecular forces, okay, while the second molecule has hydrogen bonding intermolecular forces, right, and water itself also has hydrogen bonding intermolecular forces. So this second molecule here, right, is going to have strong interactions with the water and will be able to mix more readily with the water, while the first molecule will not be able to mix with water because of the difference in their intermolecular forces. So then let's consider these 4 molecules, right? And list them, take a minute here to list them in terms of compounds that are most likely to dissolve in water. So most soluble in water is probably a better way to phrase that, right? So what is the least soluble to the most soluble compound if your solvent here is water? All right, so if we have our solvent, right, H2O, and then we have our potential solutes, right? And we're curious which of these, right, are most likely to dissolve in water, right? Is most soluble. Yeah. So to consider that, we need to consider what the intermolecular forces are in our solvent and our solutes, right? So what's the intermolecular forces that are most dominant in water? Hydrogen bonding, right? Yeah. And then what? So now let's look at the intermolecular forces for each of these molecules. So CH3OH, what's its most dominant intermolecular force? Hydrogen bonding. And then what about CH3OCH3? Dipole, dipole. And then CH3Cl. Dipole, dipole. And CCl4. Dispersion. Yep. Not give myself a lot of room right there. Sorry. Dispersion is what that says. Very poorly penned in. Right. Dispersion. Right. And so, right, if I look at the intermolecular forces in these four different solutes, right, I'd see here that CH3OH, right, has the most similar type of intermolecular force between water. And so it is going to be the most soluble, right, in water, right? The least soluble is going to be our CCl4 here, right? And then these other two will both be soluble in water, but I'm trying to remember which has a stronger dipole, right? If I had to guess, I'd say this is the second most soluble, and this is the third. So that they're kind of listed already in order in terms of solubility, with increasing solubility going to the left. But I mean, the difference between these two are going to be very minor. That you wouldn't actually need to know that. Right. Question here was what was the most soluble, right? And the answer being CH3OH. Okay. Right, and I guess should have probably done this even before starting talking about some of the stuff, right? But I've been using some of these terms: solution, solvent, solute, right? What is a solution? A solution is a homogeneous mixture of two or more compounds, right? The solvent in a solution what? And solvent is the thing that you're putting stuff into, right? The solvent typically has more amount than the solute, right? The solute is then the thing you're adding to the solvent to make the solution that you're dissolving typically in the solvent, right? Solute has fewer molecules, right, than the solvent typically in your mixture, right? Right, you can get a little, right, we can't necessarily say a solvent is a liquid and solute to say a solid or things like that, right? Because you can mix, say, two liquids together and talk about one liquid being solvent and one liquid being the solute, right? And so it's not necessarily dependent upon phases, right? And what, again, your choice of solvent and solute is typically based off of which thing you have more of, which thing you have less of is kind of what you pick as the solute versus solvent, right? But yeah. Okay. All right, let's go back. Slides here. All right, so some more solution vocabulary. What is an unsaturated solution? So that'd be a sort of an extremely unsaturated solution, right? Because if you have nothing in there, then yeah, it's definitely not saturated. Let's say this: if I added some solute to an unsaturated solution, what would you say that solute will do? Right? If I have an unsaturated solution of salt water and I add more salt to that solution, what will happen to that salt? Yep. Yeah, I mean, and in order to become saturated, the salt solid will dissolve in solution, right? Will hydrolyze, right? So an unsaturated solution, right, is a solution that, right, can take in more solute, right, can dissolve more solute, right? Unsaturated solution is not, can add more solute to the solution, right, and is able to break apart more solid solute in that solution, right? Right, a saturated solution, then how would you try to describe a saturated solution? Yeah, right. A saturated solution cannot absorb more solute. It has reached equilibrium with solid solute, right? So we'll talk a lot more about equilibrium later in the semester, right? But a saturated solution, right, is in equilibrium, right, with the ions in solution and then some amount of solid sitting around. So, right, a saturated solution of salt water, if I have the picture, no. A saturated solution of say, salt water, you'd have some solid salt sitting in the bottom of your glass, right? And the solution itself would have sodium chloride, right, salt dissolved in it, right? So a saturated solution has absorbed all the solid it can, right? And is now a solution in which the solution is in equilibrium with solid solute. Okay, and adding more solute will not dissolve in that solution. Okay, and then a supersaturated solution. Yeah, so a supersaturated solution is a solution, right, that has even more of the solute dissolved than what the saturated solution will, and because of that, it is what is considered an unstable solution, right? So a supersaturated solution is an unstable solution. Any type of minor disturbance to that solution will cause that extra solute that's been dissolved to form solid again, to crash out of the solution, as it's often called in chemistry labs, right? So, and often how you'd form a supersaturated solution is you would, as we'll talk about a little bit about kind of the solubility and temperature, right, you would heat up a solution to higher temperature where you can dissolve more stuff at higher temperatures, and then you would cool the solution down slowly. And often when you do that, the solute will stay dissolved in the solvent, even if it's past the saturation limit. It'll form this supersaturated solution, right? But again, it's an unstable situation, and any minor, you bump on the beaker that your solution is in, drop something into the solution, and it'll cause a bunch of solid to crash out and form in that solution. Okay, so supersaturated solution has a concentration, has a saturation higher than the saturated solution, right? That's to be kind of created very carefully and is an unstable case. Then what are two liquids that are miscible? What? How would you describe two miscible liquids? In terms of what happens when you mix them together. Close that is going to be our immiscible liquid. So an immiscible liquid is oil and water, right? When you mix two immiscible liquids, right, you get two layers, right? They stack up on top of each other. Miscible liquids form a homogeneous solution, right? So two liquids that are miscible will form a homogeneous solution, right? And will look like just one liquid, right? With these two liquids mixed in together. Any questions about solution vocabulary here?
No, sir.
Yep. Is there a question there? Or is that a no, sir?
No question.
Oh, okay. No, okay, that's a no, sir. All right. All right. Okay. So another kind of solubility question now, right? Oh, actually, I just answered this question. Shoot. All right, well, see how people remembered what my answer was, right? But which of the following, list the following substances in terms of increasing solubility in water? Which of these compounds is going to be most soluble in water? CH3OH will be most soluble, right? So that means, given our multiple choice answers here, right, it's got to be either C or D, right? And then, yeah, so I hear a lot of people calling out D, right? So my next question is going to be which one is the least soluble, which was CCl4, right, is least soluble. So D here, right, is in order of increasing solubility, right, from left to right. Okay. All right. So here, take a second, right, and make a list, right? So we have 4 different liquids here. And the question is, right, which different pairs of liquids will be miscible, and which different pairs of liquids will be immiscible? Okay. All right, so there's a total of 6 different pairs that we could choose from. Out of those 6, which are miscible and what are immiscible? All right. All right. So I have my 4 different liquids here, right? So I'll start off with some of the more straightforward ones, right? So for example, miscible liquids, right? You'd have things like H2O with CH3COOH. Both these molecules have hydrogen bonding, so they will mix very readily with each other. Okay. Same on the miscible side, you have C6H6 with C13H26O. Okay. Right. Again here, the right, you have, so in C13H26O, right, this molecule is a very long carbon chain, an alkane chain, right? It's a very long alkane chain, okay? Where at the very end, there's this oxygen bonded to one of the carbons, okay? So at the end of the molecule, there will be a small dipole moment, okay? But the bulk of that molecule just has dispersion type interactions, okay? And so it will be easily mixed with other molecules with dispersion forces, okay? Similarly, let's look at some of the immiscible ones, right? Things like H2O with C6H6, okay? These are not going to mix together because H2O has hydrogen bonding type interactions, and C6H6 is just dispersion, okay? And similarly, right, and same thing's going to be with H2O, and then C13H26O, okay? That's 4 out of the 6 pairs. So let's see here. Right. So I need these 2. Which other one am I forgetting here? Okay, and those 2. Yeah. 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 So I'm missing those 2 pairs and those 2 pairs below, right? And so for immiscible, also going to be CH3COOH, and we'll explain a little bit more why that there's immiscible, and then these should C6H6. All right, so to kind of help rationalize some of these, what I'm going to talk about, right, is kind of going over some stuff that were on the lecture slides, right, in the idea of, right, how things are mixing and the enthalpy of mixing and why we have this like dissolves like type term that we describe when as to whether or not 2 things will mix, right? Because the idea is, right, if I have a bunch of solute particles, right, next to each other, and then a bunch of solvent particles next to each other, right, and I want to mix these 2 things together, right, to get a mixture of solute and solvent particles, right? To do that, I got to break these things apart, right? Right. And if I were to imagine doing this, right, I could do it where I would break them apart, right, to make room for each other. Right. So I break these guys apart in order to make room for each other, and then I would, right, mix them together, right? And so, right, in a solution, it doesn't quite happen like this, where you like separate these things, you know, out and then mix together, right? This thing happens kind of simultaneously. But as just kind of a thought experiment, we can just think about it like this, right? That in order for two things to mix, this is what needs to happen, right? And so, right, if these square particles here have very strong intermolecular forces, right? It's going to take a lot of energy to break them apart, right? And let's say the circle particles have very strong intermolecular forces as well. It'll take a lot of energy to break those apart, okay? And then when I mix them together, the circles and squares have to have strong forces between each other in order to compensate for all that energy required to pull these guys apart from each other, right? I required a lot of energy to pull these guys apart, so I better get a bunch back when I mix them. Otherwise, this is not going to be a favorable type mixing, and this mixture is just not going to occur. Okay, and so again, if we think about the case where two things won't mix, right? Let's say, right, for these square particles, I have very strong intermolecular forces. Let's say there's hydrogen bonding, right? And for the circles, I just have dispersion interaction, right? Well, it will be very easy to pull apart the circles because it's just dispersion forces, so they can easily kind of be pulled apart. They're very weak intermolecular forces. I can pull those apart easily to fit in the squares, right? Well, the squares have hydrogen bonding, so it's going to take a lot of energy to pull those apart. But then when I mix them together, right, because the circle only has dispersion type forces, right, I'm just going to have dispersion interactions between my square and circle molecules, okay? Which means that I'm not going to get a lot of energy back, or I'm not getting a lot of favorable interactions when I mix these things together. So they just won't mix, right? The square molecules are just going to say, I don't want to be mixing with the circles. It's not favorable for me. I get no benefit hanging out with the circle molecules, right? I'm just going to stick with just the square molecules, right? And so they do not mix because they have different intermolecular forces, and because of that energy required to kind of break these things apart and then mix together with the other molecules, right? And so, right, think about, right, for example, right, I'd said, all right, if I look at like H2O with C13H26O, okay, right, so this does have some dipole forces, right? But if I were to try to draw out that molecule, and I'm not going to draw the entire thing, but let's just draw out a smaller version of what this molecule looks like. Okay, so these are a bunch of hydrogens. H, 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 H. Yep. All right. Right. So you have something that looks like this, okay, where I got on this large portion of the molecule, I just have dispersion forces, right? In this small section of the molecule here, right, kind of this carbon-oxygen double bond, right, I have dipole-dipole type intermolecular forces, right? So, but if I want to mix this with, say, water, right, well, I can't just put my water, right, around this end of the molecule, right? If this is going to mix and form a homogeneous mixture with water, right? A homogeneous mixture means these things mix completely, right? I don't have two separate layers. I just got one thing that looks the same to the eye, right? It looks like it's just one thing, right? Then these waters have to surround the entire molecule, right? Well, on all this area of the molecule that just has dispersion forces, my waters are not going to want to be there. They aren't going to care about those guys, right? And they aren't going to mix. And so these things will not mix together, even though there is some portion of this molecule that does want to mix, okay? And this is what forms, right? This happens all the time in biochemistry. Oh, crap, what's the term? Micelles? Right. Anyways, there are a bunch of molecules, right? Soap works this way, right? Where you have a bunch of molecules that have these long carbon chains, right? these long carbon chains, and then some part of the molecule at the end that has something like carbon with like an OH group or something, might even be something like this, right? Oh, sorry. They have these long carbon chains, right, with some end of the molecule that does interact favorably with water. So what will happen in solution is you'll actually have a sphere form where all these chains kind of hang out with each other, and then you have these different ends all around. I'm not going to write out all of them, right? But basically you form this kind of sphere, this bubble, right, where you have all this part of the molecules that don't like water on the inside of this kind of bubble that's being formed. And on the outside are the oxygens and OH groups and things like that that favorably interact with water, okay? Right? And this is how soap cleans up organic particles and things like that, because the organic particles, the molecules that have just dispersion interactions, get trapped inside of this sphere because of its favorable interactions in here, and gets washed away then with the water, as this bubble can then dissolve in water because it has these favorable interactions at the outside. So, kind of a very side tangent here. Okay, but the point being is that that's the reason why I say, even though this does have some dipole-dipole forces, right, these two things will not mix with each other and form a homogeneous mixture, because the majority of this large carbon chain, right, is not having any sort of favorable interaction with water, and a lot of water's got to break apart to fit in one of these molecules, right? I got to break apart a lot of these waters, right, to fit in this very large molecule here, to have it mixed homogeneously together. Okay. All right. So questions about this long rant I just went on? So there made no sense or made perfect sense. Don't know which. All right. So a quick question here then. Right. A solution of sugar water in equilibrium with solid sucrose, which is sugar. Right. If I add more sugar, more sucrose, and stir this stuff together, what will happen? All right. So All right, let me get this right. So I've got the people on Zoom here saying a couple of different things, some C's, E's, and things like that, right?
I would say D. If it's already saturated, there's equilibrium. Not going to get more saturated.
Yeah.
But the more sugar you add, you're going to cause the volume to grow.
Yeah, so the volume would increase. So the on D here, I throw in this word substantially to try to indicate like a large volume change, right? So right, if you're adding, I mean, I guess if you added a large volume of sucrose, so I guess that's not super clear in the problem, right? But if you're adding a small volume of sucrose, you wouldn't get a large volume change. But if you added a large amount of sucrose, then you would get a large volume change, right? And some other ones here, C and E, right? So C here, the concentration of the solution will not change, right? So first of all, in this problem, right, the first sentence that we're given is telling us we have a saturated solution, right? That solution is in equilibrium with solid. That means the solution has absorbed as much of that sucrose as it wants to absorb. So it's a saturated solution, right? So basically, right, so that's what C is saying, right? That the concentration of the solution will not change because it's saturated. So the question is, will stirring create a supersaturated solution? And the answer to that is no. Right, a supersaturated solution, to form that, you need to do things like heat your solution to much higher temperatures and then cool it down to form very, very slowly to try to form supersaturated solutions, right? But just stirring things won't form a, say, supersaturated solution, right? Right, again, in order to do that, you got to heat it up and then slowly cool it down. So in this case, it would be C here. Concentration of the solution will not change because the it's already saturated, and stirring isn't going to change that. Okay, so things like heat, temperature will change how much something can dissolve in solution, right? Right, if you bake and such, right? Sometimes dissolve sugar in water. Sugar, you got to dissolve in water. You got to heat up that sugar water solution to get all of the sugar to dissolve, right? Okay. And so, again, and that's because things, right? The amount, the saturation limit increases with increasing temperature, right? You can dissolve more stuff at higher temperatures. Okay. Yeah, and so yeah, in this, adding more solute will not change the concentration. It will keep staying just saturated, and what will happen is that solid will just go to the bottom of the solution, right, and just sit there in the bottom of the solution. Okay. If I add a lot of solute, then it would increase the solution because you'd just be displacing that solution to higher and higher volumes. Okay. All right, and while I'm looking that up, I just want to show a picture of what I was talking about, right? So this is my cells, right? Your cell membranes form like these bilayer sheets that look like this, right? So in this picture here, okay, the circles are representing the like OH groups, the oxygen groups, like these dipole ends or hydrogen bonding ends of the molecule. And then these yellow squiggly lines are representing the carbon chains, the long carbon chains. And in a solution of water, they'll form either something like a micelle here, what's called the liposome, which is this kind of dual layer thing, or just a sheet like this, a bilayer sheet, okay, which this is what your, say, cell membranes look like, okay? But then you got a bunch of proteins and other things like that floating along in this membrane, but you got a bunch of these lipids, okay, that form these cell membranes where they have a hydrophilic region, which hydrophilic means it likes water, and then hydrophobic region, which means it does not like water. Okay. So I'm going to show you a picture of what I was trying to talk about and trying to roughly draw. And then, so the answer here was C. The concentration of the solution will not change. Okay. right? If the concentration were to increase, it would form a supersaturated solution. So A and E are kind of actually the same answer, right? The concentration definitely does not decrease by adding more solid. Okay? And then here, the volume won't substantially increase because we're just adding a little bit. But yeah, so C here, concentration solution will not change. Other questions about this? See, before we do that, just because I'm talking about this concentration versus temperature and such, talking about for most molecules, if you're dissolving a solid or a gas in solution,
Oh my God, bro. Yes.
So do I keep letting it play or go?
So watch my vagina first.
why can't I?
Just so when we come back, we can get straight to it. No? Oh, did you pee though?
There we go. All right. Sorry about that. Wonderful technology. All right. Back where we were. Unfreeze this. All right. Okay. So, right, if we plot concentration versus temperature here, right? I'm using the symbol to represent concentration, right? Whether things saturated, unsaturated, or such. Okay. And if I were to do plots of different things, you'll see, I mean, it depends on the compound, but typically, right, in the lecture slides, there's some plots of these, but most stuff, whether it be you're dissolving a solid in solution or a gas in solution, most stuff, its concentration will increase with an increase in temperature, okay? Right? And below this, say, line here is representing a what type of solution? Or I guess what is that line representing, right? I'm saying, right, this line is telling us where a what type of solution is? A saturated solution, right? This is a saturated solution, right? That solid line is telling us where the saturated solution is. So if I'm below that line, if my concentration is lower than that line, then it will be unsaturated, right? And then above that line will be supersaturated, right? So I got supersaturated right above the line, and then unsaturated below the line, right? And then the lines here representing saturation, right? So again, often what you'll do to make a supersaturated solution is you'll heat up something to where the saturated solution, right, is at a higher concentration because I'm at some higher temperature, and then I slowly cool my solution off. And when I do so, if I do it slow enough, I can keep the concentration high and stay in this supersaturated region. But again, this is an unstable case. And if I somehow perturb the system, drop something into it or whatever be, knock the glass, right? It will quickly drop down to whatever its saturation limit is, and a bunch of solid will crash out of solution. Okay? All right. So, yes, so sorry, Jose, it looks like someone actually helped answer the question here, right? So again, yeah, the answer to this question was C. Again, because of the fact that stirring a solution doesn't increase or decrease its saturation limit or things like that. Okay, stirring maybe will make you get there faster, right? If you stir a solution, things might dissolve faster, but it won't change how much can dissolve. Okay, So often in chemistry labs and things like that, we stir solutions just to make things happen faster, but it doesn't mean it wouldn't happen without stirring, and it doesn't mean more things will happen because you stir, okay? It just means that it's gonna happen faster. So stirring it won't make anything happen faster, and it won't make more things dissolve, and so you'll just keep the concentration the same, and it will not change. All right. So this Henry's law example, right, is related with dissolving gases in water, right, or in liquids, right, which we've talked, I think, a lot about dissolving solids in liquids, but gases as well can dissolve in liquids, okay, right? Right, the reason why soda goes flat is because, right, what gives soda that you know, what makes it non-flat, if you will, right, is carbon dioxide dissolved in liquid, okay? Well, it goes flat because after you open the soda can, eventually that carbon dioxide is able to escape into the atmosphere because it's no longer in some pressurized can or container. And if that carbon dioxide escapes into the atmosphere, it's not coming back. And eventually the concentration of CO2 in your soda decreases and it becomes flat, okay, as we like to call it, right? And so the description of the concentration of a solution, right, or concentration of a gas in a solution to the pressure of the gas above that solution is given by Henry's law. And what is Henry's law? Related with the concentration of the solution equals something. Yeah, let's see. Yeah, it's related with Henry's law is constant and the pressure of your gas. Now, I'm doing this right here, and I'm thinking, did I mess this? Concentration equals K times P, right? I'm now freaking myself out thinking, did I switch S and P around? Don't think I did. But yeah, concentration. Yeah. No, that's fine. Yeah. So this is your concentration, right? This is your Henry's laws constant. And then P here is your partial pressure of the gas. Okay, so this is a linear relationship, right? If you plot the pressure of the gas versus its concentration, right, you will get some straight line where the slope of that line is equal to what? Equal to K, right? Right, this is the equation for a straight line, right? Y equals mx, right? And here's the slope, okay? So slope of this line is K, right? You have a straight line, right? And this is how K is measured, right? K is a constant that depends on the gas and the solvent, right? So it's very much dependent upon what your solvent pair are, okay? And K is something that needs to be determined experimentally. And this is how they do it, right? They measure the concentration of the gas and the pressure of that gas, right? Above the solution for a bunch of different values, plot that, and then, you know, find the slope in order to determine what that constant is, okay? So, the question here then related with that, right? Related with, you know, soda, talk about pop, depending on where you're from, cola, I don't know, right? Different names for the same thing, depending on what region of the country you're born in. Right, but you have some soda here that has a partial pressure of CO2 of 4 atmospheres at 25 degrees Celsius. In that can, with that pressure of 4 atmospheres, concentration of CO2 is 0.14 molar. The question is, what is Henry's law constant for CO2 in water at 25 degrees Celsius? And then the second part of this question is, what is the concentration of CO2 in the soda after the bottle is open and it's equilibrated to the partial pressure of CO2 in atmosphere, which is 3 times 10 to the minus 4 atmosphere. And for those who have the handout, who are here in class, right, or if you're online, you printed it out or something like that, have it open on your computer, right, this is the very first question on that chapter 13 exam. Okay. All right, so again, what is that equation related with Henry's law constant, right? The very first thing we're asked is to calculate that constant. So what is that equation? S equals AP here, right? K is what we're looking for, right? So if I rewrite that, I can put K equals P divided by S, right? Plug in, nope, what did I do? That's wrong, sorry, right? Divide both sides by P, right? To get K equals S over P, oh geez, right? And so now plug in my concentration, right, which I've been told the concentration was 0.14 molar over a pressure of 4.0 atmospheres. Okay. And so plug that in. You get that K equals 0.035 molar per atmosphere. Okay. So that is my value of K. And then the next part of the problem, the question is what is the concentration given partial pressure of 3 times 10 minus 4 atmospheres? Okay. And so I do, right, what is the concentration, right, is what we're looking for. Again, Kp, plug in now the constant here is 0.035 molar per atmosphere. And then my pressure, right, I'm told is 3.0 times 10 to the minus 4 atmospheres. Okay. And so you multiply those things together and you'll get a concentration of 1.05 times 10 to the minus 5 molar. Questions about how we did this problem? Okay, so where did I get P? So for the second part of the problem, right, I'm asked find the concentration of CO2 after the bottle is opened, and now the partial pressure is 3 times 10 to the minus 14. Okay, yeah, so that's where I got that other pressure was from the problem here. Tells us, right, that once the bottle is open, right, what is the what is the concentration when that partial pressure of CO2 is now 3 times 10 to the minus 14 instead of 4. Okay. All right. All right. So another example of this, right? We have a question here with the pressure of CO2 of 1.5 atmospheres. Its concentration solution is 0.015 liters per atmosphere. Oh, not liters per atmosphere. That should just say liters per mole, or moles per liter. What is those units? Sorry. Oh no. Sharing. Let me just fix that. I don't. Moles per. All right. There. That looks a lot better. I don't know what I was doing with those units. All right. There we go. Sorry about that. All right. So again, I have the pressure of CO2 is 1.5 atmospheres. Its concentration solution is 0.015 moles per liter. What is the concentration in water when the pressure of CO2 is now 2.8 atmospheres? All right. So there's a couple of ways you could go about trying to solve this problem, right? We can approach this problem like we did the last one, right? We can use this information up here, right, to solve for K, the Henry's law constant, then use Henry's law constant to solve for the concentration. The second part here, right? I can also do this from the fact, right, that I'm going to call this P1, S1, P2, S2 here, right? That P1 CO2, right, is related with K times S1, right? And then P2 CO2 is equal to K S2. And I can use the fact that, right, I can just divide two equations from each other, right? And the K's cancel, right? P1 CO2 equal to P2 CO2 equal to S1 over S2. Okay. I'm trying to solve for S2 so I can then plug in things, right? And do 1.5 over 2.8 equals 0.015 over S2 that we're trying to solve for, right? And you do that, right? And you can solve for that unknown concentration is going to be 0.028 molar, okay? But you can even get that also from the fact, right, that because, again, there's this linear relationship between pressure and concentration, right? My pressure increased from 1.5 to 2.8. My concentration, right, that's like 15 times 10 to the minus 10 to 28 times 10 to the minus 10. My concentration will increase from 1.5 to 2.8 as well, okay? Because of the numbers, right? This is 1.5 atmospheres and this is 0.015 molar, right? Without even plugging numbers, I know that this final concentration would be 0.028, right? But again, it's just because of this linear relationship, right, between pressure and concentration that I don't have to solve for K. I can just use the ratios of those pressures and concentrations to solve for the new concentration, okay? Right. If you want, right? Again, you can do this, you can approach this however you'd like. You don't have to solve it in this way. You can solve it by first solving for K and then using K. That's fine, more than appropriate. No problem with doing it that way, right? I just wanted to present another way you can look at it and think about how to solve a problem like this, okay? In different approach. Questions about how I got this answer here? So on Wednesday, we'll go into a lot more detail about these different types of concentration units. We'll do lots of examples with these concentration units and converting between them and such. I just want to, again, remind everyone that, right, videos going over in more detail about Henry's law constant and, you know, like dissolves like and all these other things, right, are online, are available to view, okay? Right, and if you have questions related with the homework, right, which the homework for this chapter is due today, right, on sapling. Now, I know I do have like a homework assignment on Canvas, but that's just there to be able to remind you that, hey, do the homework on sapling, right? There's no actual homework on Canvas, okay? It's just a reminder for the sapling homework. And then later I'll upload your sapling homework scores to Canvas under these assignments, right? So they will eventually, the grades will be put on Canvas from sapling at a later date by me, okay? Right, but again, please review the course materials, right? Before class, after class, come to me with questions. If you have questions about homework, right, I'm happy to help try to answer them. If you have questions about the quiz, right, after it's been due, right, I'm happy to answer those even as well, right, to review any questions maybe on the quiz that you're confused about. Happy to go over that as well in class after it's due. But yeah, so please, again, feel free to come with questions so we can discuss things, go over things together here in class. Otherwise, I will see, I guess the people who are here in person, I'll see you guys in 2 weeks. Otherwise, I'll see you on Zoom on Wednesday, right? And again, don't forget to turn in your, the participation questions on the back table as you leave, okay? If anyone on Zoom has further questions, you're welcome to ask. I apologize if I'm not super quick answering Zoom questions during class. I'm trying to get better at that.
I didn't get the participation question. But I did take some.
Back at the table there. You want to just grab that and take a minute to answer those? I'll wait just a minute longer here for people on Zoom for any questions. If I don't see any, or hear any, I'll end the Zoom call. But yeah.
I had a question.
Okay.
I was trying to email you about it, but for some reason the email wasn't going through. Like it kept going to my outbox. I don't really know what that is, but it kept doing that. But
through Canvas?
To go through Canvas?
Well, that's what I'm asking. Were you doing it through Canvas, or were you just doing it through how you normally send out emails?
Yeah, I did it through Outlook.
Okay, Outlook. I'm not sure. Are you? Let me. Just make sure.
Yeah, I even tried forwarding it to you again and things like that, and it just kept going back into my outbox. I have no idea why.
Right, are you using SRY, like SRY18 or SRYOST should work. I'll type them out also here.
Let's double check right now.
Right, either of those things, right, at txstate.edu, right, should work. Yeah, if not, I'm not exactly sure why that's happening. Maybe you can try sending me a message through Canvas and see if that will at least work. It's another option. For people who are on Zoom, if you are just doing online only, you'll have weekly participation kind of questions posted every week that you have to answer. If you're attending on Wednesdays, then you'll have your own questions on Wednesday that you'll have to answer, right? And so, yeah. So,
Okay. Well, my question was on the math, on the math review homework for Sapling, there was one I'm almost 100% that I got it correct. And so eventually, whenever I put give up, because I was like, there's no other way I would do this, I put give up, and it showed me the same exact way I put it in my calculator, but it was a different answer. And I was like, is it because of did I not have it in scientific or what? And it's I don't know if the math was, my calculator was wrong or their math was wrong. So that's why.
Yeah, I mean, so Sapling, especially with some of the questions on the math review, could have issues with the how your answers typed up. It can be really annoying in particular, and so it could be something like that. There could have been a mistake on Sapling. If you have kind of the question or something and you want to email me about it, I can take a look into it and see what potentially the issue was. But yeah, so it could either be somehow a random formatting thing with submitting the questions that can be kind of annoying, or maybe a potential error on Sapling. But But yeah.
Okay. And I had another question, but this is more like a request. It's if you could like maybe open the quiz for maybe more than just a day, because I work. So yeah.
Yeah, I'll look into it. I've been trying to figure out how to do it. I don't like the idea of having it open for too long. People potentially telling other people about what questions are on there and potential cheating on like that. And so that's why I try to like not have it open for very long. But I also try to have it span, like that's why I tried to have it span like yesterday into today or something like that. But I'll take a look at kind of when that is and stuff and maybe try to play around with that. But
Okay, thank you. Yeah, because I did miss the first one because I was working. All right. Well, then that's it. I will try to email you that question to hopefully it'll send this time. I'll go ahead and try.
All right.
All right. Thank you.
Thank you.
I have a question on the sapling actually as well.
Okay.
So on Canvas, you had that it was just the sapling chapter 12 that was due. Then I didn't realize till later that it said something, or the math review and the ungraded assignments.
Oh, yeah. So those things are like listed on sapling, like, but those aren't actually graded. So they have like a due date because it's sort of like, you know, if you're going to work on them, I suggest you work on them here. You can always look at the sapling stuff after they're due and still mess around with it. But yeah, all those things were ungraded. Every chapter will have additional problems, and they're just there as additional practice problems for those who want to look at them. Right. But in terms of your actual grade, there's just the chapter problem like that. It's a graded assignment. And,
okay. I got nervous because I was like, oh, I missed those then.
Yeah, no. Yeah.
Okay.
So it does warn you about due dates for them and stuff. But again, I just put due dates on there just as sort of like, you know, if you're going to look at these problems, I suggest looking at them, you know, now. But again, they are open after they're due. The questions are still there for you to look over and things like that.
Okay. Thank you.
Yep.
I just wanted to make sure.
All right.
Have a good rest of your day.
You too. All right. And let's see here, and then Jose here. So if you're supposed to attend on a certain day, you know, like if there's certain days that you can't make it in class and just have to attend online, don't worry about it because, right, I'm going to drop a number of kind of attendance scores or whatever at the end of the semester, sort of like I drop a quiz where you can just miss a quiz for whatever reason, and that's fine. You can miss sort of these participation points for whatever week, and that's fine. But just with how things are kind of designed, right, if you're supposed to be in class on Monday or on Wednesday, right, that's when you'll get those participation points. And then if you've elected to not show up at class at all ever, then you get the stuff assigned online through Canvas. So that's kind of how that works. So yeah, hopefully that kind of answered the question. Hopefully you're still here. All right, so I am going to close up now, and I will see you guys in person or on Zoom on Wednesday.